Hello gentlemen, welcome to section 7.5, which is entitled Phase Changes and the Cooling Curve of Water. Today we're going to talk about changes of state, changes of matter, two in particular, melting and freezing. Now melting is often referred to as fusion in chemistry. That's when you have a solid phase going into a liquid phase, and as we know, we're putting in energy to have that process happen. That's an endothermic process. So this happens, melting happens at the melting point. The melting point is the temperature at which a solid changes to a liquid. At the melting point, there is enough kinetic energy to cause particles in the crystallized structure, the solid structure, to break apart or break free from the forces holding them together in that crystallized structure. So they have enough kinetic energy and vibration to finally break free. That's the activation energy that we've always been talking about. Now, this melting happens when we add in enough energy for this to happen. This energy is called the heat of fusion, also known as the enthalpy of fusion. And this is the symbol for it, H sub FUS for fusion. This is defined as the amount of energy that a substance must gain in order for a solid to change to a liquid. So a certain mass of this solid must gain a certain amount of energy in order to have the melting process happen. Now I say gain, we know that gain symbolizes an endothermic change. Now the opposite of melting, we know, is, of course, freezing. So freezing is also sometimes referred to as solidification or crystallization. This is when you're in the liquid phase and you go into your solid phase. This happens through an exothermic process. Energy is being released, let's say, from water, and as water transforms into solid. Now, this happens at the freezing point. The freezing point is the temperature at which a liquid changes to a solid. Simple enough. Now, here's a key point. This occurs at the same temperature as the melting point. It's the same temperature, it's just in a different direction. You melt going one way, you freeze going the other way, but it all happens at the same temperature. Now the energy, this requires energy to freeze something. But it doesn't require you to gain energy, it requires you to lose energy. So this energy, or this situation, is called the heat of crystallization. This is the energy released when a unit liquid mass of a substance freezes. So when a certain unit of mass is trying to freeze, it will have to lose a specific amount of energy, and that energy is defined as the heat of crystallization. Now, the heats of fusion and crystallization are equal in magnitude. As I just said, they happen at the same temperature. They're equal in magnitude, but they have different or opposite signs. For example, the heat of fusion of a substance could be 250 calories per gram. That's positive. And for that same substance, the heat of crystallization would be the same magnitude, 250, but it's negative, meaning we are releasing heat. So remember our phase change diagrams, not our phase change diagrams, excuse me, our reaction diagrams, reaction curves, where we had its reactants and they gained some activation energy and formed the products. Well, we knew that our change in enthalpy, when it was positive, it was endothermic, which is what fusion is. When our change in enthalpy was negative, it was an exothermic process, and that's what crystallization is. So take that with you. Now, a little cumulative summary here. So when heat energy is involved in changes of state. I'll start that one. So changes of phase always occur with a change in heat energy, as described in the past two boards. The material, whatever substance you're talking about, can gain heat energy, which is endothermic, or it can lose heat energy, which is exothermic. The amount of energy gained or lost depends on which phase change is taking place. Here we're talking about melting versus solidification or crystallization. We'll also be talking about vaporization versus loss of words. Oh, condensation, excuse me. Now, the heat content of the material changes during a phase change. Again, the heat content, meaning the heat can be added or heat can be released, that changes during a phase change. But the temperature does not change during a phase change. So if heat's increasing or being released, decreasing, but temperature does not change, what is that heat doing? Well, let's look at that here. When energy is absorbed during an endothermic phase change, like fusion, it's used to overcome the attractive forces between particles. So, for example, when ice melts, the energy being put in is being used to break the intermolecular forces between the particles involved. And it's not being used to increase the kinetic energy of those particles, but simply to break the intermolecular forces between them. So that's why the temperature stays steady, because the energy isn't being used to increase the average kinetic energy, but it's being used to break the intermolecular forces between those particles. And when energy is released during an exothermic process, or exothermic phase change, it's due to the formation of their interaction between the particles. So when ice forms, we're creating new interactions between particles, and when we create new interactions or new bonds, we release energy. That's an exothermic process, so the energy is being released, and it's not being used to really slow down the average kinetic energy, so temperature stays constant. So gentlemen, take notes on this. Hopefully this was clear. A lot of this is review, but some of this is new in terms of how it's phrased.